Hello, I am Mr. Shrum, and I'm back again with one of these mastery test walkthroughs. And we're going to look at the one about predicting motion, using forces to predict motion. Now, the first question deals with, well, at least when it comes up on my teacher walkthrough, it asks about Galileo. And what did Galileo contribute to the study of motion? Yeah, what did he contribute? Well, he was the first to systematically study or look at forces and motion. Yes, while Newton did develop his laws of motion, Galileo did contribute things as well. Then we had the second question. If you pull an object toward you, what force are you exerting? Well, a big clue is that you are applying a force. Anytime you push or pull, you are applying a force, and that is known as a what? An applied force, okay? So hopefully you know that one. Now, the next situation is Tanya. We have Tanya, and she's picking up a leaf from the ground. So a leaf. And then she holds it at arm's length. So we'll draw that out. Tanya. Tanya holds the leaf. And then she lets it drop. And it falls to the ground. So what is this force pulling it to the ground? Well, we know that gravity is pulling that leaf. Okay? So that would be the gravitational force, right? Because Tanya's not applying a force, she's just holding it up in the air and then it's falling to the ground. Lucas rubs a plastic ruler on his sweater. So we got Lucas. Wah, wah. Lucas. Yeah. He's got a plastic ruler. Then he rubs it on his sweater. Plastic. Rubs it on his sweater. Rubs a ruler on his sweater. Then he waves it over a pile of shredded paper. And it is attracted to the ruler. So he rubs a ruler on his sweater. Then he waves it over tiny pieces of paper. And then that ruler attracts these tiny bits of paper. So what force is attracting the paper to the ruler, right? Remember that he rubbed it on his sweater. So that would be most likely electrical force. Think of when you rub your hair against a balloon. And then it sticks to it. That is also because of the electrical force. Okay. Next question. Ethan pushes, let me move the paper. There you go. Pushes a wooden box across a carpeted floor. So Ethan, bam, 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 pushing a box on carpet. Then he pushes it along marble floor. Okay, so we have carpet and then marble. And he thinks it's a lot easier to push it on the marble than it is the carpet. So why? Why is that easier on marble? Marble's very smooth, right? Carpet can be rough. Not smooth. Another way to put it. Well, that means the box on the carpet will have more friction. We'll experience more friction, but on the marble floor, we have less friction. Okay, so which answer corresponds to this. Less friction on marble, more friction on carpet. All right. Next question. You're asked about forces, and this is a very conceptual question, all the way back to our beginning lessons. Forces. They have strength and direction. Because they are vectors, not scalar. Forces have both magnitude and direction, their strength and direction. Then you're given a drop-down menu in the next question. It says a box is at rest on a table. What can you say about the forces acting on the box? Well, there is a normal force pointing up, and the force due to gravity, the gravitational force pointing downward. It's sitting and it's at rest. At rest. Equilibrium. What kind of equilibrium? Static. And that means the forces are balanced. Are balanced, okay? Easy peasy, easy peasy. Now you have another drop-down menu. Now we're told that Amy throws a softball. Yeah. Through the air. What are the different forces acting on the ball when it's in the air? Okay, so here's the ball in the air. There is an applied force from Amy. As the ball moves, it experiences drag. Drag force. There's applied force, a drag force, and then also the force of gravity. Okay. So another way to draw that out, F applied, F due to drag, F gravity. Okay. Applied force from Amy, drag from the air, and then gravity. Kind of a given. There's three things acting on that ball. Okay. Last drop-down menu type of question. We're talking about Maurice or Morris. He pulls on the end of a spring scale, and then he lets go of the end and then observes the spring snap back into place. What force restores the spring to the original shape? So let's draw it out. So there's a spring, pulls it this way, and then what's the force that restores it? Well, when we're dealing with springs, there's a restoring force, and that is elastic. So anytime you're dealing with springs, think of elasticity. If you stretch something, it wants to come back. If you compress something, it wants to go back to the original length, right? Go back to the lessons about a spring. If this is still hard for you to understand, but the elasticity of the restoring force makes the spring go back to its original length. And then last set of the questions, we're talking about Matthew. And he runs 4 tests, and then you're shown 4 pictures of this box. And then the arrows are the forces acting on the box. And the size of the arrows tell you how large the force is. So test 1 looks like this. Test 2 looks like this. Test 3 looks like this. And then test 4 looks like that. And then you're asked which one illustrates a balanced net force. Which one looks like a balanced net force? Well, this first one, 2 forces in the same direction, that's not balanced, right? Nope. Wrong. The second test, one's going this way, one's going that way. That's not balanced. This one is close, but this arrow is bigger than this. So that means there's more force going this way. So that is also not the case. The only balanced test is that one. Because there are opposing but equal forces. And that is the end of the predicting motion mastery test walkthrough. I hope that was helpful for you all. And if you have any questions, send me a message on Canvas and I will help you as much as possible. Thank you and goodbye. See you all next time.